Welcome. My name is Pavel Bauer. I am full professor in the Faculty of Electrical Engineering, Mathematics and Computer Science at Delft University of Technology. The topic of this lecture is power converters in motor drives, particularly DC motor drives. The outline of this lecture is as follows. We will first get to know various types of power converters. After that, we will go through different components needed to realize power converter. Special attention will be paid on the core component, which is power electronics semiconductor switches. Based on the knowledge on the components, the basic building blocks, half bridge and full bridge, will be studied. At the end of the lecture, we will look at how the edge bridge can be modulated to realize the voltage of the motor demands. Let's first take a look at the various power converters you may see in motor drives. Based on types of input and output, that is to say direct current or alternate current, we may categorize common power electronic converters into a DC to DC converter, AC to DC converter, or DC to AC converter. AC to DC converter is often addressed by the other name of rectifier, and DC to AC converter is often addressed as inverter. This slide shows the circuits of these power converters. We can see that these circuits are built based on the various electrical components. Let's continue to explore different electrical components inside the power converters. These components can be categorized into passive components and switching devices, switching components. As can be seen on the screen, passive components include inductors, capacitors, and transformers. The functionality of the inductor and the capacitor in the power converter circuit is usually to store energy in its internal electromagnetic field and smooth out the voltage or current ripples. The transformer is able to introduce a voltage ratio or provide galvanic isolation between the two sub-circuits. The switching components are able to regulate the direction of or on-off of the state of circuits. They include diode, thyristor, power bipolar transistor, power MOSFETs, and IGBT. As an example, the diode only gets to forward the current while blocks the reverse current, and there is no way to turn it on or off actively. Bipolar junction transistor, on the other side, can be turned on and off by controlling the current into a gate, and therefore it's called gate current control device. The MOSFET and IGBT can be turned on and off by the voltage between the gate voltage, so are gate voltage control devices. They are also mainstream power electronic semiconductor devices in the modern motor drives. Let's move on these two mainstream switching components. IGBT is short for the isolated gate bipolar transistor. Its behavior is determined by the relative voltage difference between its gate and emitter, VBE. If voltage between gate and emitter is larger than the threshold, IGBT turns on and behaves as a small voltage drop. Otherwise, the VBE is below the threshold, it turns off and behaves like an almost infinitely high impedance. IGBT does not allow reverse current, so in motor drives, an antiparallel diode is always needed to allow the reverse current to flow. IGBT can provide very high rated voltage and current, but has moderate switching speed. The MOSFET is short for metal oxide semiconductor field effect transistor. Similar to IGBT, it turns on if the gate to source voltage VGS is higher than the threshold voltage, but behaves as a small resistance when it is on. Otherwise, it stays off and behaves as an almost infinitely large resistor. The power MOSFET always has an internal diode, so no external antiparallel diode is needed. Compared to IGBT, it has faster switching speed, but comes with a lower rated voltage and current. In this course, we may just simplify both devices as an ideal switch controlled by its gate signal and neglect their switching transients. Then it comes to the question, how to construct power converters from these components. A commonly used basic building block in motor drives is the half bridge. It is formed by the two power switches connected in series, fed by a DC source, with its output on the middle of the two switches. As shown on the screen, if the top switch S1 is turned on, while S2 stays off, the output between the node A and neutral would be the same as the DC input voltage, VDC, while that between the node A and the DC source midpoint would be the half of the VDC. If S1 is off while S2 is turned on, VAN will become 0, while VA0 would be minus VDC divided by 2. In one switching period Ts, if we let S1 on for the time D, duty cycle Ts, and let S2 on for the rest of the period, we would be able to obtain an average of these times VDC between A and N. By repeating this switching sequence, we realize that so-called pulse width modulation, PWM. In practice, this can be realized by comparing a reference voltage, Vref, with a voltage between 0 and VDC to a triangular carrier waveform, charging in between VDC and 0 with a period of Ts. If Vref is larger than the carrier, S1 is turned on, otherwise S2 is turned on. Then we may call the ratio between S1 on time and the switching period, the duty cycle D of S1, and represent it with the symbol D. When the average output voltage between A and N would be the D times VDC, and that between A and 0 would be the D times VDC minus half of the VDC, or simply D minus 0.5 times VDC. By connecting a DC motor between the half-bridge output node and the power supply, ground, we realize a two-quadrant motor drive. We call it two-quadrant because although the half-bridge allows our reverse current flow from the motor back to the source, but its output voltage is always positive. These two circuits show the operation of it and the first quadrant and the second quadrant. With the setup as such, we are able to turn the motor in forward direction, both as a motor and as a generator, but not able to turn the motor backwards because the voltage polarity is not reversible. To make the DC motor drive reversible, two half bridges can be used to form a so-called H-bridge. With the two half bridges connected in parallel to the same DC supply and the DC motor between the two midpoints, the motor terminal voltage now is the differential output of the two half bridges. If we control the two half bridges so that the left one has a lower output voltage compared to the right one, the motor voltage polarity is reversed, so it can be rotating backwards. The remaining question is how to realize the PWM so that the output voltage would follow our reference. Looking closer to the H-bridge, we can see S1 and S2 forms the left half bridge, while the S3 and S4 form the right half bridge. One way to operate it is to have S1 and S4 switching always together, so are S2 and S3, while both pairs of switches complementary. This way of operation is called the bipolar modulation, because the output voltage is always switching between positive VDC and negative VDC. Let the duty cycle of S1 and S4 be D1, and that of S2 and S3 be D2. Since both pairs switch complementarily, D1 plus D2 must be 1. The average output voltage is then the differential voltage D1 times VDC minus D2 times VDC. The above-mentioned bipolar modulation can be realized as shown on the block diagram below. On the screen, it shows the simulated waveforms of the bipolar modulation of the H-bridge. It can be seen that one pair is switched with a 67% duty cycle, while the other one with 33% duty cycle, giving rise to an average output voltage of 100 volt from a 300 volt DC bus. The output voltage switches between plus minus 300 volt. Thus, the modulation is called bipolar modulation. The other way to operate the H-bridge is the so-called unipolar modulation. In this modulation scheme, switches on the same half-bridge, S1 and S2, or S3 and S4, switch complementarily. Each half-bridge just provides the positive half of the negative half of the output voltage. Therefore, V0, V output, is a switching either between VDC and 0 or between 0 and minus VDC, depending on the polarity of the desired voltage or desired output voltage. Compared to the bipolar modulation, the unipolar modulation shows less current ripple because lower change of the voltage rate. Assuming S1 and S3 are with duty cycles D1 and D3 respectively, we can see the average output voltage would be in the differential voltage between the two half bridges, that is to say D1 VDC minus D3 VDC. This modulation scheme is described by the block diagram on the screen. As we can see, the left half bridge is modulated to provide the positive half of the reference voltage, while the right half bridge takes care of the negative half of the reference voltage. The simulated waveforms of an H-bridge with unipolar modulation are shown in the screen. As you can observe, the left half bridge provides plus 50 voltage between the output and the midpoint, while the right half provides minus 50 volt, resulting in an average differential voltage output of 100 volt. The output voltage just switches between 300 volt and the 0, so it is unipolar. Compared to the previous bipolar case, the current ripple is reduced by half. Looking back, we have learned knowledge on both components and circuit levels. We know now how a half bridge is formed and how to realize H-bridge based on a half bridge. We also touched upon the two different modulation schemes for the H-bridge. In the coming lectures, you will learn more about how to use the H-bridge to control a DC motor with feedback-based control and measurements. Hereby we conclude the lecture. Thank you for watching this video. Good luck with the rest of the study.